Okay, so now we are going to start section 1.2, which is called or titled Elements, Compounds, and the Periodic Table. All right. So first things first when we talk about this. I mentioned this in the previous video in section 1.1, but said that I didn't want to go there. Didn't want to get into too much detail. An element, basically we can say that an element is something that we find on the periodic table. Okay, so what does the periodic table look like? You all have probably seen this before, but we're just going to look at it briefly. And I'm going to toggle back and forth to this a few times. Here's our periodic table. This lists every known element. We are up to 118 now, which is oganesson. Okay, those names are relatively new for these. But anyway, now we'll talk about in chapter 2 actually what all of these numbers mean and what some of the different things in the periodic table mean. But if we look at a block on the periodic table, let me point out a couple of key features to you. All right, we have a number up here at the top of the block. We're not going to focus too much on that now. That's called the atomic number. There again, that is chapter 2 material, but that is called our atomic number. The atomic number identifies the element. Hydrogen always has an atomic number of 1. Gallium, I'm just picking something at random. Gallium is always 31. Then, for now, the next thing that we're going to focus on is our symbol, right? Now, let me notice here, hydrogen is H. Lithium is Li, just for example. I'm just picking a few at random. Carbon is C, so on and so forth. All right. Let's talk about that a little bit. Okay. Those are called the chemical symbols or the elemental symbols. They are 1 or 2 letters. Now, something important with this, when they are 1 letter, that letter is always capitalized. So when we write hydrogen, we always write hydrogen as H, not as H, right? No, we don't do that. If they are 2 letters, the first letter is capitalized. Second is lower. Okay, so if we have lithium, just for example, that is one that I talked about a minute ago. Lithium, notice we write it capital L, lowercase I. All right, in this class, you are not going to need to memorize the entire periodic table. That's something that I'm going to sidetrack a little bit. I know that some of you all may have taken a high school chemistry class where you had to memorize or learn the periodic table. That's not necessarily something that I see a lot of value in us doing or spending the time to do. just because, number one, you're always going to have a periodic table on your exams. In fact, I will, at our first lab meeting, I will show you the periodic table that I will. No, wait, your exams are online. Sorry. So you will actually have access to the periodic table website. That's the one that I provide to you. So, anyway, so sorry, scratch that. But yeah, you will have the periodic table that I showed you just a moment ago. The other thing about that too is that, so you'll always have access to it. If you use these stuff, if you use this stuff, you'll learn the elements that you need to learn. Okay, but nonetheless, there's still a few that I want you to learn. So some of our big ones. And of course, these symbols, they're again going back to the symbols. A lot of times they are perfectly logical. So just for example, hydrogen, this is one I want you to learn, has the symbol of H. Makes perfect sense, right? Carbon has a symbol of C. Now, there again, capital H, capital C. Oxygen is O. Nitrogen is N. Yeah, those are some of our biggies. Those are some of the most plentiful elements around. They are also the most plentiful ones in your body. Two other big ones. There again, I want you to know these. Phosphorus, which is P. There again, just perfectly logical. Sulfur is S. Now, a couple others though that I want you to learn. So this is a big one. They're again very common. Sodium. And of course, sodium, following along the same lines as the previous ones, we can see that it makes absolute perfect sense that sodium would have the symbol of Na. Right? Similarly, and you don't need to, this is not one I expect you to know, but similarly, it makes perfect sense that lead has the symbol Pb, right? No, not at all. So a lot of these, if you look at them and you wonder where on earth did that name come from? Oftentimes, elements that don't have a particularly intuitive symbol, it actually comes from the Latin name for the element. So the Latin name for sodium is natrium. So when we say that, that actually makes that makes a lot of sense that if this is natrium in Latin, then Na is going to be the symbol. Similarly, lead is plumbum in Latin, so Pb. All right. Along those lines, though, I want you to know these 6 elements. And then I also want you to know sodium, potassium, which is K, sodium, potassium, and chlorine, which is Cl. That's an easy one to remember. All right, that's what you need to learn from the periodic table. All right, let's revisit our periodic table again, though, and let's look at some other features of it. Let me find my cursor so that I can share the screen with you. All right. So let's revisit our periodic table. Okay, we can divide our elements up a couple of different ways. So on the left side of the periodic table, we have the metals, right? Now, what's the dividing line between the metals and the, or sorry, left side of the periodic table, we have metals. On the right side, we have nonmetals. Okay. They are divided by, if you can see here in sort of this teal color, by elements called metalloids. Sometimes you'll see them called semi-metals. These are not ones that we worry about too much in here. So we're going to kind of sidestep these and just say everything to the left of these. So if I is a metal, so if I ask you what's aluminum, you can always say aluminum's a metal. I'm not going to ask you about something like antimony, SB. There again, another symbol that makes perfect sense. But anyway, now just remember this specific relationship or this general layout that to the left we have metals, to the right we have non-metals. Because when we get especially into chapter 3 and talking about compounds and bonding, distinguishing between metals and non-metals is going to be a big deal for a lot of things. And being able to look at the periodic table and just at a glance know whether something's a metal or a non-metal is going to help you out a lot. All right. Now, something else that we need to think about on the periodic table. If you look, these are arranged in columns and in rows. The rows are called periods, by the way. That's where the name periodic table comes from. Right, what do those tell us? Well, first of all, the periods tell us a lot about things. There's a lot we can get from periods that we're not actually going to talk about in the this class when we talk about electron configurations and things like that. That can tell us a lot about reactivity, but we don't do electron configurations in here. We don't really talk about orbitals. So we're not going to worry so much about that. But the groups are a big deal because elements that are in the same group have similar reactivities, right? Everything that's in group 1, which by the way, we call the alkali metals, everything in group 1 has a lot of common reactivity. Now, we are going to learn about something in chapter 3 called valence electrons, and we'll talk about why valence electrons dictate that reactivity. But just know that lithium, sodium, potassium, rubidium, cesium, and francium all are very similar in how they react. So just to briefly go across here, we're not, we don't focus too much on groups in here, but these are called the alkali metals. These are super reactive, at least in their elemental form. We usually find them as ions. That word I realize probably doesn't mean anything to you yet, but it will in chapter 3. Our next one, alkali earth metals. Sometimes we see these in their elemental form. Magnesium's fairly common as an element, just for example. But these are fairly reactive, not quite as reactive as our alkali metals. This whole big group here in the center are called the transition metals, right? Chemistry of those, transition metals are super common. There are some of these you see and encounter all the time. Iron is everywhere. Copper, of course. Silver, gold, some of the ones like that. But anyway, the chemistry of transition metals actually can get really complicated. And so a lot of times when we talk about things in here, we don't really focus on transition metals, or we just kind of leave them out of our discussion. We can use them for some things, but there's information you will have to be provided to be able to use them. There again, hold that thought for chapter 3 when we get into talking about bonding. All right. Beyond that, so the only other group, or the only other 2 groups that I'm going to kind of mention and note are these, which are the halogens, chlorine, chlorine, bromine, iodine. These are also extremely reactive, to the point that they're, again, you typically encounter them in compounds or as ions. But interestingly enough, this group here are this group is called the noble gases. These really are not that reactive. Helium, neon essentially don't react. We get down into some of the bigger ones and we can start forming compounds. Not a lot until we get down to about xenon or so, but really helium and neon in particular are just not reactive. They don't form compounds. And there again, the reason for that will all make sense in chapter 3 when we talk about valence electrons. All right, notice that these groups have numbers. Now, this is the current accepted numbering system. Leftmost group is group 1, and then we number 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth across until we get to 18. Now, there is an older numbering convention that I still find very useful, and I still teach it and talk about it, where we call group 1, group 1A, group 2, group 2A. Then under that system, group 3 is group 1B, so on and so forth. But those are transition metals. We ignore those for now. Going with that A and B nomenclature, we skip over the transition metals. We get over here and we get to group 3A, then 4A, 5A, 6A, 7A, and 8A. The reason for that, there again, I'm just kind of planning that thought now. Those numbers get us directly to our number of valence electrons. There again, don't expect that to mean anything to you at this point, but it's there. And so just kind of keep that thought in the back of your head also. All right, but those are our elements. Now, let's talk about compounds. All right, what is a compound? A compound is two or more different elements chemically bonded together, right? Now, not physically bonded, that's a mixture, but chemically bonded. Right. There are more different elements chemically bonded together. Now, when we look, just to kind of make a point of this, if we have two or more of the same element, so just for example, O2, that is the normal elemental form of oxygen, looks something like this. This is not a compound, right? This is just two oxygens bonded together. Same thing for nitrogen. But if we look at our favorite compound, favorite and extremely important compound, water, we see that we have a hydrogen bonded to an oxygen that's bonded to another hydrogen. Another really common one, carbon dioxide. All right, now, all of these lines and dots and things like that I'm drawing here, I'm drawing them to be consistent and correct, but I don't expect them to mean anything to you yet. They will, again, in chapter 3. But anyway, in a compound, we have elements combined together, and they are combined together in a fixed ratio. Now, we give that ratio as a chemical formula. Here's how we give that. You all have seen these before, or you all have encountered these before. So just for example, for water, water is made up of hydrogen and oxygen. Each water molecule contains 2 hydrogens and 1 oxygen. If it does not contain 2 hydrogens and 1 oxygen, it is not a water molecule. So we write H, we write O. Now, to indicate that we have 2 H's here, we put the subscript 2 here. So H2, and then O. We only have 1 O, so we don't need to, we don't put anything there. We don't put a subscript on it. CO2, similarly, we have 1 carbon, we have 2 oxygens, so CO2. We could have the compound carbon tetrachloride, which we write CCl4. Okay. Compounds can be simple, they can be huge, right? They're all over the place in size for what we could consider a compound. We typically deal with simple ones in here, simple and small ones. Although as we get deeper into some of the chemistry, especially chapter 4 and chapter 10, we'll start looking, and chapter 6 also, we'll start looking at some fairly complicated molecules. But by that point, you will have seen enough to be able to break them down and make some sense of them. But anyway, that is a compound, right? We write this as a chemical formula, right? There again, subscript, we write the elements, we put subscripts to tell how many of each of those elements there are. Okay. Now, something else that I will mention. This is not a concept we necessarily formally teach in this class, but when we have certain types of compounds, just for and those certain types we'll talk about some in detail. Just for example, if I were to write the formula Mg2Cl4, so Mg2Cl4, I could actually simplify that down to MgCl2. That simplification is called the empirical formula. Now, that works for this. This is what's called an ionic compound. There again, keep that name in the back of your head. But that doesn't always work. So just for example, if I write the compound C2H6, I can't simplify that because CH3 is a totally different thing and actually a compound that doesn't even exist. But anyway, so yeah, just mention that sometimes we can simplify these, sometimes we can't. For our purposes, I'm going to tell you that we're never going to simplify them. Just to kind of keep that idea around for you and to make things simple for you. Just want to mention that though, in case any of you are thinking and wondering if we can do that. All right, that gets us to the end of 1.2.